So let's welcome our next speaker, Shrijeet Mukherjee. He's the co-founder and CTO at Enfabrica. He is a distinguished technologist with a long career spanning computing as well as networking. And he'll be talking about he'll be talking about foundational networking silicon for the accelerated computing era. Let's welcome Shrijeet. Were you able to connect to Zoom?
No,
Yeah.
this audio first with Devendra, it's working very nice, but for locally it's not working.
Really?
Yeah, check.
Should
Do we need to do any
Sound
setup?
check, sound check.
Okay. Okay.
Very good. Thank you.
Can you guys see and hear?
Yes, I think we're good.
Okay. Can you hear?
Yes,
Amir,
yes,
can you- Okay,
all good, thank you.
Okay, good.
Perfect. So I have to get over the blushes, but give me a second. Thank you for that rather flattering introduction. I'm going to start with saying, how many people here have heard of Enfabrica? That's more hands up than I thought, so I have to skip my opening joke. Anyway, so what I'm going to do is I'm going to talk about some things that hopefully either you guys will see as will hear it and say this is obvious, and of course I know it, and this doesn't need to be repeated, or you'll say this is completely wrong, and we'll have a good, healthy debate about it. The point of the talk is to talk about how we in Enfabrica ended up building the product we are building, and the genesis or the thought process that informed us into getting there. So we'll start with a little bit of history. Right? If you go back a long time, maybe the 90s, 2000s, computing was built around these things called supers. The concept of a super was big coherent systems. In fact, the last system I worked on at SGI was a 2000 node, 128 ATI graphics cards, now AMD, in a CC/NUMA tight domain. It sounds amazingly similar to certain products that were released in the last year. If you look at the progression of such systems, I always find it helpful to look at sort of what happens over a decade, right? So NumaLink 5 and NumaLink 8, about a decade apart, almost doubling in bandwidth, almost flatline on latency, which is a very good thing if you're trying to build a big coherent system. What were the characteristics of systems like this? There were about 2 to 4 processor sockets. They had SMP in that socket, and then NUMA everywhere outside. Why did you have to go to NUMA? Because tight coherent systems didn't scale well. The cross-node performance became network performance. In fact, NUMA is networking effectively. So you have to worry about what topology, how many paths, what resiliency, what happens if you went into half state or split mode or things like that. But fundamentally, in this model, all accesses are IPC. In fact, the previous speaker was talking about how everything should be a load store long-term design. And what we found was when you start getting into the 2,000, 4,000 node systems, that last access was very, very hard to guarantee. And most importantly, the entire system is coherent, which means at very large scale, you will have very variable latency. Now, granted, if it's 800 nanoseconds versus 100 nanoseconds, it doesn't seem a lot in terms of absolutes, but it's still a high variable or high amount of variability. Then you had 3D toruses, you had dragonflies, and a whole bunch of other topological investigations that people had to do to get these systems to operate well at scale. And finally, much of the operating system, much of what went into making these systems work well was about page management. Because at the end of the day, shared memory and shared resources sounds great. No one wants to go access a shared resource across multiple hops every time. So ultimately, at the end of the day, there was an operating system that was working behind the scenes to make sure that your placement and your affinity between memory and CPU was good. Come into the early 2000s, and people started realizing that building these things at scale became problematic. Cross-fabric scheduling became a factor of complexity, and it became a thing that was very hard to debug and operate well. Application level tuning became extremely hard. You had applications that were running great at 16 nodes, Then you ran it on 2000 nodes and you saw things going all over the map and you didn't even know where to look. The most amazing thing about load store variability is that debuggers don't show it. Trying to figure out where the problem is one of the hardest things you can do. And you had to build specialized custom tools to do it. The answer was the rise of Borg, the Google model, right? Do everything with a highly distributed design, shard everything. And if you look at what the bandwidth sort of landscape looked like, it didn't look that bad either. So over a decade, standard TCP versus RDMA Rocky, which is where most of the high performance workload has moved, has done about a 10x improvement. You're on the same ballpark at 12.5 gigabytes per second versus 13.3. Latency is much, much worse, but that's all right. And the reason why that's all right is because the programming model looked like this, right? You had lots of worker threads. Your absolute performance was guaranteed within the worker thread. Everything else was a question of building data pipelines. And data pipelines were just RPC problems. Latency really didn't matter. I mean, of course it matters, but it wasn't a first order problem. The other thing about this scheme was that it had significantly better resiliency characteristics. You could lose entire shards and not care. You didn't have to worry about keeping your workload running consistently and coherently across every node in the system. It's great if all your problems fit within one of these nodes. And the other thing that this programming model introduced was instead of worrying about processor accessing memory or processor accessing a resource, everything was wrapped in an RPC library, and you had the chance to intercept and redirect and redefine what these calls look like. Let's come to 2020, let's say 2. We have the ML monsters, right? These domain-specific accelerators, things that are just taking over the world. Interestingly enough, we started in 2020, and we used to go around and tell people that we want to solve the ML problem. And more often than not, we got told that we should go look at really important problems to solve instead. But if you look at the class of the solution, if you really just squint hard, you realize the solution that has evolved is sort of an amalgamation of the two models. You have a scale-up domain and a scale-out domain, and they both need to operate well. But there are some things that are changed that are very different from when the previous attempt was made to solve this problem. The first is that the programming model has been, I don't want to use the word compromised, but has been compromised. You don't have to worry about the programming model because people are morphing their programming model or their application to the programming model that makes their hardware characteristics come up and are optimized for it. Excuse me. But they do want the resiliency of a cloud scale system. So you sort of are trying to come up with this model where you have tightly coupled computation, resiliency of a cloud scale system. This is the new problem. And then let's not forget memory. Supercomputers, the supers, was built around load store. That was the primary communication model that they were optimizing. And therefore, strict control over hierarchy was a requirement. You couldn't just say, there's memory over there, it'll take a few microseconds, get it whenever you can, and then I will continue this next stage of my pipeline. You had to be very predictable about it. NUMA machines, like we already discussed, stretch these limits a little. Distributed cloud systems, on the other hand, are all packet-based communications and RDMA interfaces, which are the programmer's interface. Now, what is creating a problem is that this design, the distributed compute design, is getting stretched because different protocols are coming into place, different congestion models are coming into play. And the question that now is upon us is how and what should be the new programming model? And most importantly, at least most importantly from our perspective, is there a best of both worlds? Let's also understand what the world actually means. So this is a taxonomy that I'm trying to hoist on the universe. If you like it, please reuse it. And And the taxonomy is mostly the right column, right? The left column is just a statement of fact. But what is interesting here are these three things. So like if you look at the hierarchy, right, you're seeing the latency, the bandwidth, and sort of the programming model on the rightmost column. What is interesting is that the moment you get out of this dereference pointer work, you are able to provide higher bandwidth, more capacity at a further distance. A lot of effort in the past few years has been sort of invested into making this layer provide the characteristics of this layer. And that is hard. Switched fabrics are never going to be as good as directly connected systems. So one of the things we want to observe and sort of build around is that there is a place for every tier in this hierarchy. But what is required is that promotion through the hierarchy is the most important characteristic. And that for the first time in the world of physics, we are now at the spot where the bandwidth at a further distance is actually higher than the bandwidth close by. Dr. Sharma was just talking about DDR bandwidth and how it's not really growing as fast. Ethernet bandwidth, on the other hand, at 800 gigabits per channel, is already double a channel bandwidth relative to DDR. So what can we do with that? So let's again look a little bit at how the systems are being built, right? So this is a simplified diagram. In the real world, there would be a big cloud of switches in between and so on and so forth. But like Gilad mentioned earlier, you have rail optimized green Ethernet links and NVLink style coherent blue interconnect links between your compute elements. This is the world that sort of is evolving, and people are trying to build these systems out to larger and larger scale. The persistent competition is going to be, does the blue domain increase or the green domain increase, or did they both increase together? In current systems, one characteristic you'll notice is typically the bandwidth on all the interfaces are roughly balanced. As in the scale up and the scale out domains are roughly the same number of gigabytes per second. However, the computational topology, Gilad was mentioning that as well, is rather important. And the computational topology is fixed. The way people are doing it today is rather than say, I need bandwidth and I need to be able to do bandwidth on demand, they're saying, I'm going to just avoid contention. I'm going to build rail optimized designs. And then I'm going to make that topology work into my collective communication libraries and work backwards from it, because I've already pinned the topology up front. And it's designed for max performance. Cost is an afterthought. One thing we should have learned from computer systems architecture over the years is for mass adoption, for widespread mass adoption, cost becomes a critical factor. And you can't just keep over-provisioning everything. Another application, which is very similar, it looks like machine learning or ML in nature, is very large databases, which was an area that we also wanted to focus on. And very large databases topologically look a little bit like this. You have some coherent domain that's going to carry your master index and your master tables, and you have a whole bunch of clients down here that are connecting over a network and trying to extract the data and provide it. You could think of this as an inference problem if you really wanted to. The problem here that you see in cloud scale systems is that you end up creating larger and larger memory pools for this guy, because the context, the size of the context that it has to operate is increasing every day. And you don't have to build it that way. It doesn't have to be that this guy is carrying a very large context at all times. One approach to solving this problem is the CXL approach, where they're saying, I'm going to create larger shared pools of coherent memory and partition it up front and make it all work out. We will see if that works out. That's a complex problem because it involves a whole bunch of ISAs, low-level CPU accesses, and the memory that's backing it. And you have to tune it and make it work at very high performance at all times. But we'll see. So that's the background. Those are the problems we were looking at. That's the state of the world we were looking at. So what do we think is the solution? So this is our solution. We call this the accelerated compute fabric. It's a single chip solution. It has lots of 800 gig Ethernet ports on one side, lots of PCI CXL ports on the other side. Inside it, it's got two switching planes. It's got a PCI switching plane, and it's got a Ethernet switching plane and a PCI switching plane. And sort of the magic trick of the system is this thing that we call copy engines. These copy engines are capable of looking at PCI memory and making packets, RDMA, or looking at packets and making memory with their data placement. So what you are familiar with as GPU direct, think of it as something that does anything direct. If there's a memory space, we can write to it. If there are memory spaces, we can aggregate over it. So you can build very composable memory transfers using our copy engines, and there are tens of thousands of them. Additionally, this device looks like effectively a NIC to interfaces to systems connected to it, or rather can look like a NIC, and it looks like a TOR to devices connected above it. So, oh, sorry. Yeah, I should keep an eye on that screen as well. So I guess I already said those words, so I pause here for a second and let people read it. But yeah, so the idea is that it's got 800 gig Ethernet interfaces on one side and lots of by 16 PCI ports on the other side. And the idea is that it can operate as a very high performance and very high capability L3 router, a very high capability CXL PCI switch, but can also impose data movement on top of it. As an example, what Dr. Sharma was talking about, right, where with CXL 3.0 and back invalidate and the ability to do direct IO or UIO, they are avoiding the need to send traffic into the CPU, but it still requires one of your active components to generate the reads and the writes. One of the things we are offering is by having the ability to do all the data movement in our chip, you're offloading that functionality as well. So you can think of it as sort of a DPU function, but it really is a very tightly integrated memory mover architecture. So what can you do with that? What kind of solutions can you build with something like that? So one simple answer is to build effectively an accelerator agnostic fabric, something that has a very high performance transport, which is software defined and actually software managed. And this transport can straddle different accelerator architectures at the same time. It's also a very high performance network, like we talked about, operating in multiples of 800 gigs or in multiples of 100 gigabytes per second per port. It can actually, and we don't show that here because it's not pragmatic for us to think of it that way, but it can also be the coherent link as well. So you can imagine that instead of having the specific fabric link, you can use us and our bandwidth as the way to also do the coherent communication between devices. So the question becomes, why do it this way? Like, why this way and not the alternative design, which we call the stovepipe design, right? The one accelerator, one NIC, to a TOR kind of architecture. The first and most important part is that this allows us to do effectively better scheduling. It's work conserving, it's bandwidth conserving. So if there is a producer and a consumer that is not using the bandwidth that is hard allocated, we can reassign that. And we have learned over the years that that's a good thing. It cuts down on network latency because what this is doing is effectively saying there is one layer of cable that's gone, right? You're not serializing out of the NIC into the TOR and then up again. So you've just taken that whole layer out. In fact, in reality, the efficiency is even higher because there's another whole layer of packet parsing that goes away because we parse early on ingress in both directions. It lowers TCO. This one is rather obvious. You've removed a whole bunch of components and replaced it with one. And the data movement, because it is wide, or the data movers, because it sees the aggregate of all of the network ports and all of the host ports or the GPU ports, we can shuffle, we can densify, sparsify, we can multiply, we can do all kinds of things to the data movement, which is actually what is required, but you cannot do if you're doing it per endpoint. Again, because we are now creating queues that are, let's call it application thread facing, but these queues on the other side are aware of the network. These queues are going to effectively implement and enforce a much nicer quality of service model than what you can get with anything else. Let me say that a slightly different way. If you look at standard QoS designs, the NIC and the switch are always guessing what the other side is doing. There are obviously custom designs where much more information is provided on the sideband, Slingshot being one of them, where you can do something better. But a traditional switch and NIC don't have that luxury, doesn't exist. You're just looking at packets and trying to figure things out. In our case, inside our fabric, we have complete visibility into the state of each of queues in both directions. So our QoS is 100% precise. We do not move data. We don't move or even pull data unless it's required, unless we can do something. And finally, this bandwidth matching problem, which is what you actually need. At the end of the day, all we are trying to do is move memory to its correct destination. What this device can look like is effectively a NUMA controller that's coherent with everything attached to it that can move data remotely using RDMA. That's sort of the ultimate goal that we want to get into. And why this is useful is now the long links, the links between the ACFs, which is Ethernet based, does not have to meet all the requirements of a long NUMA network. You can use standard Ethernet rules, you can use multipathing, you can use lag, you can use active standby, things that have been perfected over the years, and get that scale up. Now the question, or scale out, I should say, the question that should be in your minds is, yeah, that's just RDMA. But what we are doing that's different is, by increasing the scale up domain, we are creating the tier in between in which memory can be stored and memory can be accessed from, that allows us to hide the latency to the last tier. So how does this play? What can we point to and say, this was a beneficial thing for us to do? So let's look at two interesting characteristics. One is scale and the other is resiliency. So if you build a design like this, you can build, as an example, let's say you had a 4K cluster. And let's say for the sake of argument, to achieve that 4K cluster, you require a 3-tier network. With a design like this, you can actually achieve the 4K cluster with a 2-tier network. Primarily because we've absorbed tier 1, and secondarily because we can spray across a wider set of links and thus make it such that each link is a smaller contributor on a wider radix system. That's the first advantage. But the second advantage, which is far more important, is that that also gives you resilience. It allows us to fail some of those links that we are sending the traffic across and continue. Because the problem with many GPU systems today, for example, is that you lose that cable to the NIC that's connected to the GPU, you lost the GPU. And since you're doing distributed compute, you can't really just say, I didn't care about the data anyway. Let's just keep moving. This solution allows you to address both of those requirements, the depth of the tree, therefore the variability in performance and the scale of the cluster you can build, and the resiliency attributes that are associated with it. This is mostly a marketing slide, but a simple way to think about it is, this is a NIC that can do very fancy things. And most specifically, it can do a configurable, user-defined transport with congestion management. We have obviously the standard solutions in box, but you can extend it into various different dimensions. And it can also do, in addition, like I said, a whole bunch of very specific memory movement and memory targets that are otherwise very hard to achieve. So as an example, right, like a single NIC cannot possibly write to 2 PCI ports or to 2 PCI devices, because you would need to go across somewhere. We can, and because we have a very wide surface, we can write to a very wide set of ports. the use cases for large training fabrics is a little bit easy to understand. The left one is a very typical traditional 8GX, DGX type solution. You have, traditionally, you would have seen 8 GPUs and 8 NICs and a bunch of PCI switches in between. We've just taken all of them out, and what you get coming out of the ACF is Ethernet, and everything else is in the chip itself. The solution on the right talks about things you can do that are a little bit more, let's call it refined. So things like in-network compute, things like collective acceleration, you can now do because this is a point of aggregation. There's a device here that can see everything underneath it. And because we can do very optimized transactions like broadcast and multicast, we can do things that you can't otherwise do in a traditional NIC, and you have to look for an aggregation point that's somewhere further away in the network. For people who've looked at collectives, right, I mean, it's always very attractive to say, put it in the network, but then you say, oh God, now I have a synchronization problem. The advantage of doing it in a solution like this is that the synchronization is tightly controlled within the ACF itself. Another very interesting use case is the ACF as a global memory solution, right? So if you think of it, or what this picture is trying to show is that you could have, let's say tier 1 was your processor architecture. Tier 2 was memory that was attached to an ACF attached to that processor architecture. And tier 3 was somewhere over your RDMA network. One solution we enable, right? So while the CXL community is trying to do what it's trying to do, and it'll get there, and as Dr. Sharma said, traction is good, but it'll take a while for new models to get fully adopted. And we support it. We support whatever CXL is going to bring to the table. But before CXL adoption is complete, what we already bring to the table is an ability to effectively create this tiered memory with built-in promotion. So if you say that I never want these processors to touch memory outside its local memory, ever, then what you do is you basically create a second tier of a much larger locality in memory attached to the ACF, and you create the third tier, which is your entire network of a significantly larger locality in every system that you have on your network. And by having a very high performance promotion path where pages that are going to get hot will get promoted from this tier 2 to tier 1, and locality that's going to get hot will be promoted from tier 3 to tier 2, you can make it such that your processor's performance is always going to be optimal and peak because it's only talking to tier 1. And we take the effort of moving the data from 3 to 2 and 2 to 1 based on signals from the hypervisor, and we have some hardware support for that as well. A very direct use case for something like that is LLM inference. Like one of the problems you have to solve today with inference is locality. How do you figure out which user is going to land on which GPU, and how do you save and restore context for that user, assuming you're actually trying to multiplex your GPU because after you paid, oh, we have one more. After you've had, so I should have noticed you getting anxious. So the problem that you have is if you're trying to keep multiple users on your very, very expensive GPU, context switching becomes a problem and context spinning becomes a problem. So a picture of this graph on the left is showing what happens if you just do it the naive way, right? You're just basically queuing or pinning people to machines and saying, whenever the last job finishes, I will restore your context and get you to go. That's, I mean, this is obviously rather obvious once stated. If you don't do that, and if you say that I'm going to store context at a higher level and I can move those in place at hundreds of gigabytes per second, which is way inside the 10 microsecond budget that most inference applications will let you have for getting your context up and going, you can make the average delay or the average wait for context to be significantly lower. And the simulation data we had showed about a 50% improvement or in GPU utilization, or you can achieve the same SLA with half the number of GPUs, which is, I hope I don't have to say rather good. And the last use case I have is Memcached, right? People are building large and large databases all the time. Your classic memcached was built such that you went from slow to fast memory and then accessed it through RPC. What we can build instead is a scalable set of web servers and a scalable set of memcaches. And these memcaches, like we were talking about earlier, are basically going from the level 3 to level 2 to level 1. And the ACF is able to orchestrate all of that autonomously as long as the web cache requests are provided to it, which is exactly how memcached works. So creating the locality and creating the promotion algorithm is rather simple. And that's something we will provide when we have the systems to show. So to close, because I have to talk about product at some point, this is a sample box. This is not our box. We are a silicon company. But anybody who thinks any of this is interesting, this is a box that's orderable now, and it's in manufacturing. And it will allow you to do all kinds of things. It has the ability to be a central node into a GPU network. It can be a central node into a memory distribution network, or you can just use it as a very large Ethernet plus PCI CXL switch. And that was the end. This is what a rack would look like. I'll just skip past it and stop here and see if there are any questions, or have I put everybody to sleep successfully?
That's very interesting talk. Let's thank the speaker. So unfortunately, we are running